honor to be presenting at such a prestigious platform that's the Capella Days. And greetings to everyone who has joined from different time zones to our session, Capella for Modeling CubeSat, a tailored SE process for leveraging model-based systems engineering. I am Suvigya. I work with BlueKei Solutions as MBSE engineer. Um, Before I move forward, a bit more about BlueKei Solutions. The company provides consultancy services for enterprises and startups regarding the digital engineering transformation in the engineering practices through systems engineering methodologies and MBSE. We work with various verticals, that is aerospace, automotive, healthcare, and industrial. As an MBSE engineer and an aerospace engineer, I work with aerospace, mostly aerospace projects. With my time here at BlueKei, I have gained exposure towards modeling with SysML, now with Arcadia as well. Moving forward to Dhirendra, could introduce.
Hello, everyone. And I am Dhirendra Singh, and I work as an MBSE engineer for BlueKei. And I have my academic background in mechanical and aerospace engineering. And yeah, and I've been modeling. I've been with BlueKei for a year now, and I've been modeling different systems and have been working with robotic systems, aerospace systems, and stuff. And yeah. Back to Suvigya.
Okay. So moving forward, um, Stuti, if you would like to introduce yourself here.
All right, sure. Sami will introduce. However, greetings everyone. Like Suvigya said, just checking the chat. Everyone's logged in from various time zones. So thank you for being here for the session. We are looking forward to, how you find it useful and knowledgeable, and look forward to the interaction post the session. Myself, I'm a systems engineer, been practicing it for 14 years, both academia and industry. And right now, it's been 3.5 years with BlueKei, based here in India, but working with global different industry sectors. And back to Suvigya now.
Thank you. Moving forward to address what all we'll cover in this talk today. This session would be divided into 3 parts. That would be introduction to CubeSat, SE and MBSE, where we will go through, we will have a touch base over what the CubeSat as a system, what are the complexities involved in such a system, and how SE and MBSE can be tailored, or why should it be tailored for such a system. The second section would be the methodology followed for modeling for the system CubeSat in Capella, an overview of the model generated, and the third section would be what are the value additions observed from such a Capella model, what would be the scope of such a system in SE practices, ending with the conclusion itself. So to start with, CubeSats today in our industry, in the space industry, what we know of CubeSat, as you all know here, it originated with sole purpose of technology demonstrations or academic purposes, as a replacement of as an alternative for satellites, like a cheaper alternative, a smaller alternative for those for the complex huge satellites here. Now with the commercialization of CubeSats, we move towards more complex science missions, the recent developments, as we know, there are swarm missions being planned, like Starlink here, interplanetary missions such as the Mars mission being planned by NASA for interplanetary deep space purposes, and all of such developments leading to commercialization and standardization of what we know CubeSat as a system. What we all know of a CubeSat being 1U, 3U, as we might have often heard. It's mostly just 10 centimeter into 10 centimeter into 10 centimeter 1U CubeSat stacked together to fulfill defined purpose, defined missions. Uh, that lead to data accumulation or sensing over a region, various applications being defined for such missions itself for the CubeSat. Today, what led to the modeling effort for this CubeSat, we have this problem statement. That's that's the weekly revisit of various cities and having a downlink station at another city, gathering images for a defined period of time, weekly revisits to such locations, and so on. So with this problem statement, what drove the modeling effort, the purpose of the study was to understand the impact of this this evolving technology, what we see in MBSE, to the industry that's growing every day. So even in our home country, in Indian fraternity, what we see space industry getting uh, uh, expanding every day. How it can catch up with such technologies, and how um, these MBSE models can contribute or can have a scope in the complex processes, the development of such complex systems. So moving forward, when we say CubeSat and complexities, I want to have a touch base on what do we mean when we say CubeSat as a complex system, because we are aware that these are like smaller satellites that usually have uh, defined purpose, not so elaborate, but as these CubeSats are simpler to say have defined subsystems that can be usually 3D printed, that give some that reduce the cost. But even if the cost is reduced, the efforts aren't. So moving forward, let's see where does the complexity lie in in a CubeSat development activities. When we talk about SE and MBSE, it's for the complex systems. So CubeSat as a mission, CubeSat mission itself can have various complexities, as we know. What we discussed in the earlier slide, the mission itself, we know we need to collect images, we need to have weekly revisits. But what's the objective of it if it's only sensing the only sending images for the infrastructure or agriculture purposes? Those objectives can bring in uh, even more complexities to how your CubeSat has to function. Uh, and with that defined, the launch and deployment of such a CubeSat, how would it? As we know, usually CubeSats are secondary payloads with a primary bigger satellite. It's usually a ride share with more CubeSats as well. There can be different means to it, and for such applications, you usually have to you have to reserve a slot on such launch vehicles itself before even you get started with the development itself, even before you know what your system would be. That even brings constraints to the launch dates, the timeline itself. Uh, Moving to operations and data management, once it's placed in the desired orbit, what would be the command and data handling on board, even on ground, how to coordinate these operations can be even further complex itself, and to autonomy and to have an autonomous procedures on board for error handling, that that in case whatever goes wrong in the scenarios, the operational scenarios, the what if cases that the CubeSat itself has to handle on board. Because as we know, CubeSats, as they get deployed, it has to be first time right. It cannot be like as we know of say aircrafts, that it's not a like land takeoff. It's usually that's for the aircrafts, but for satellites, once into space, they are on their own, and it has to they have to be reliable systems that can handle such different scenarios related to the operation itself. Further going to communication and ground stations, that can be say one ground station handling this mission operations, or it can be multiple, have to have a reliable communication link, and as well as safety and compliance for as these CubeSats are getting integrated to a launch vehicle. It has to comply to the vibration standards, the radiation standards. You have to the CubeSat developers have to show a proof that the system is safe to get integrated. So these operational aspects add complexity, and it's a need to translate these into the CubeSat as a system, so that when we talk about subsystem integration, miniaturization, what we know of CubeSat, how these different subsystems such as ADCS, the power distribution unit, all of it has to work in harmony. But for that to be a success, there is a need for translating these mission objectives, these constraints itself into the system, into the design of the system, so that it's not just one certified system, but it's a success overall towards the mission itself. We talk about research constraints, we talk about testing and verification for CubeSat as a system, but that being driven by the CubeSat mission itself, and systematically towards the definition of the system here. Uh, it's a need. There is a need to have a systematic way to manage such complexities. And further, with these complexities, we come across various challenges as well, be it regulatory compliance, be it risk management, integration and compatibility, be it one of the primary focus and a challenge here would be software development as well, for the autonomy and the error handling. So these challenges need to be usually, as we know, are need to be handled when throughout the CubeSat development process. So how does SE and MBSE help manage these complexity, help manage these challenges? Let's get more into detail of those. When we say the common challenges that we saw previously, the SE approach would influence us to target such challenges as technical and management, and how we can harmonize the dealing with such challenges in a systematic way. We call it what we know with CubeSats. There can be multidisciplinary domains interacting with each other on on the integration of various subsystems that can lead to technical challenges when it comes to integration. There can be licensing involved. There can be configurations involved for the missions or for the system that can lead to management challenges. So SE, that is systems engineering practices, it would have once defined, it would initiate a formalized way to deal with these challenges systematically. So for this study, we adopted the Vee model itself for the SE practice. For a CubeSat, it could start with mission analysis, leading to requirements engineering, architecture development, further disciplinary model-based design, software design, unit testing. and towards integrated systems testing, the commissioning for the system itself, and the maintenance and operations could be the end of the life cycle of the system. So with this Vee model, we are trying to integrate both SE and MBSE for the CubeSat, the life cycle of CubeSat development in terms of SE and MBSE with say with mission analysis. As we start, what are the operations involved for the CubeSat that is on the right side of the Vee. We start addressing that itself in the from the very beginning in the left side, which further get translated into the system as requirements for the mission, further getting decomposed into the subsystems itself. What are those requirements being allocated to for a subsystem in an architecture, and so on. So with the Vee model approach, as we know, the SE approach, we have the left side of the Vee in supplementing the right side of the Vee for the activities that are going to be executed the down the lane for the life cycle. They usually start with the left side, the planning itself, so that the iterations on the right side can be mapped with the left side of the Vee. So, for example, requirements itself at the left side get verified by the right side of the Vee, and so on. So we know that software itself, for these systems, usually have agile life cycle of their own, and not the Vee model. But further down further in these slides, we will see how this such models can even enable or supplement the separate life cycle of such software side as well, in regards to a holistic view of CubeSat as a system. Uh, when we move further to MBSE, it usually comes with its benefits. That's the traceability, the impact analysis, the change management itself enabled because of such models. So this is quite a representation for the digital thread being established with MBSE. So when we say mission analysis, it can lead to the operational scenarios that are being usually constrained by some stakeholder, or being concerned because to some stakeholder, that these stakeholders give the stakeholder requirements for such scenarios. What are they expecting the CubeSat itself to perform, say in a scenario where it's only concerned about the uplink of the mission? How these stakeholder requirements get translated into system requirements, to system functions, and so on. So this is quite a representation of how MBSE allows to maintain such traceability, to have like a digital thread in the model itself, to see the coverage of how your system is being realized from an abstract idea of an operational scenario to even a unit, to a component itself. Moving forward, I would like to hand over to Dhiren for the second section of the slides.
Yeah. Okay. So, regards to the modeling or to the scope of the model that we are going to discuss in further detail, it's mostly on the conceptualization part, or the conceptual phase of the system development, where we have taken mission analysis, requirements engineering, and architecture development, and we have tried to map that to our Capella model. And then we have tried to see, okay, what where we can place the model and how we can use it during the processes, right? Yeah. So moving on to the next slide. Yeah. So now we're actually going to see how the system model contributes in dealing with those technical changes and the management challenges that we have, right? So so it is when we start thinking about a mission that the needs and wants of the mission and the product development become major challenges or constraints going forward, like having high reliability when thinking about communications between satellite and the ground station, right? Limited launch opportunities act as time constraints for development and testing, and complying with standards and regulations like EMI, EMC, vibrations, thermal constraints. So these factors are all external to the system, but they have to be considered as they pose constraints to our satellite, and they have to be incorporated in the system during the system development. Uh, can we move on to the next slide? Yeah. So this leads to us identifying stakeholders and external systems in the form of operational entities like regulatory bodies, launch vehicle service providers, integrators, etc., and mission capabilities like clicking images of the area of interest through business and mission analysis process, and stakeholder needs and requirements analysis process, so that no compliance and quality requirements are missed. And the Capella model helps us to capture all of this under operational analysis, and it aids us in connecting missions to the systems. As an input to the operational analysis phase was the problem statement that we received, from which we started to model the sequence of operations and identified our operational activities like transporting the CubeSat to the launch site, placing the sat in the launch vehicle, performing maneuvers for attitude correction, etc., and leading into identification of external entities to capture our system context. Having a connection between the entities and operational capabilities helped us to scope down the mission capabilities that are system of interest, or the CubeSat that needed to perform, like communication with the ground station, right, surveillance or remote sensing, as well as the assistance it would need to for those identified mission capabilities during its operational scenarios, right, uh, giving it a view at the system of system level. And all of this led us to having a refined ConOps, and with a well-defined problem statement, a more refined problem statement, and led to us identifying our high-level mission capabilities and operational activities that would aid us into the product development going further. Going to the next slide. Okay, so after having a well-defined problem statement using operational analysis, we now have to start thinking about the system definition, right? Which brings forth more challenges like budget constraints that we have here, power management, limited resources. That is resource allocation in terms of missions that will be later translated into functional partitioning of functions that we're going to identify during our system analysis and architecture phase, that would then again be translated into software requirements and our hardware requirements, right? So as we do so using system requirements and definition process, and capture that under the system analysis and mission capabilities. To the next slide. Yeah. So under system analysis and capabilities, we start converting our mission capabilities into system capabilities that our system has to perform, right? And for that, we start identifying our stakeholders, our actors, and then we start connecting those operations or the operational capabilities to those stakeholders or the system entities, the system actors that we've identified here. So, for example, for remote sensing of the region of interest, we have this high-level mission capability, which is then broken down into CubeSat having to obtain the orbital velocity of, let's say, X kilometers per second, visiting the region of interest, maneuvering for alignment, collecting the images, and then sending those images back to the ground station. All right, linking with stakeholders and entities, and leading to taking this is leading us to taking the first step or into planning for acceptance testing. Right. Then all the high level operations are converted into mission functions. If you can see the third image right in the bottom, so all of these high level operations are converted into system functions. Example, collecting the images capabilities. So that capability is refined into having the ground station initiate the process while the CubeSat responding to that command, and then allocating the required resources, and then start clicking the images the of the region of interest. So all of this led us to having a well-defined system boundary, uh, which also helped us scope down into, okay, the functions, the high level functions that our system need to perform, right? We then had our preliminary system requirements that we wanted. We had a preliminary interface definitions. We also identified our TPMs, and this was actually, and this initiated, or this was the first step into a V&V process planning. Okay. uh, to the next slide. Okay, so the preliminary system and interface definition led us to tackling integration issues, like integration and integration compatibility and supporting integration planning. And all of this was actually supported by having a very well structured, or let's say a very well documented architecture, or a well defined architecture we that was made in the next step, right? Yeah. So we started identifying the logical components of the architecture, where logical functions of the system were identified. They were mapped to the model, where the CubeSat was broken down into having a communication system and a subsystem, which is responsible for handling functions of recovering the command in ground stations, and a data handling subsystem responsible for processing and executing that command. Okay, so the architecture led us into having this operational scenario where we can we broke down the operational capabilities of the system capabilities, then into system functions that were then broken down into many more sub functions, and then allocated into these different subsystems that our CubeSat has, and even the ground station has, clearly differentiating, okay, what is it that the system needs to perform, and what is it that the external systems need to perform. And the communication between these functions, or the system functions that we have identified, were also placed, uh, yeah. So and the flow of communication between these functions was also identified and captured here in the models. And this ultimately led us to, so this was the logical part of the architecture. But then there is also the physical part of the architecture, where we started identifying, okay, what are the physical components that could actually realize the functions that were identified in the previous section, right? So these physical these physical components, while we're capturing these physical components, the architecture also actually helps us with helps us with the trade study part of the process. Like example, if we are going to choose an antenna for our communication system in a satellite, right? It could be an S-band it could be, sorry, an S-band patch antenna, it could be a UHF, it could be helical antenna, it could be anyone. But uh, the constraints that we had from our stakeholder needs and stakeholder requirements then flew into these functions and properties, and into having a defined system element. And that could actually help us lead into helping choosing the right component, right? Yeah. So, and ultimately having a good architecture also helping a good architecture also led us into having well defined ICDs and integration plans, which going forward can actually which can follow a smooth integration process and a smooth V&V process going forward. Yep. So yeah, going back over to Suvigya. Thank you.
Yeah. Thank you, Dhiren. I would like to emphasize here, with this representation, what we see here as inputs to the modeling activity, and the outputs itself in the blue boxes, while the green boxes representing the systems engineering activities that could follow through with such outputs. So even when we define this for our the AC process itself, with Capella, we observe that it supports the transition from these phases, as it has a systematic way to have a trace between, say, logical to physical elements, transitioning logical to physical elements, and realizing and maintaining a trace of how the previous phase is being realized in the next stage. With that, moving forward, some other value adds that we see with the system model of this scope being added to an SE adoption process was the functional chain that Capella provides. So as we all know, functional chain being defined would be the sequence of functions being executed in an order to define the performance itself for such an activity. So even in Capella, we see I'll start from here. So with what we had defined, what we were discussing in the previous slides, having a software having a separate life cycle itself, be it an agile life cycle on the side. So with functional chains defined at a system level, we observe that it could supplement the concurrent development of say software itself, in a sense that say a functional chain at operational level is defined for uplink and for downlink. So so various teams working towards in silos for the functional chain, the activity itself. What can be the what if scenarios? What are the expected functions if say the communication link is lost, be in the uplink chain? What happens if the communication is lost in the downlink chain? Even when that is being elaborated in silos for this chain, it gets reflected back as in a holistic view at functional architecture level. So for systems engineers to respond to such overlaps or such conflicts, if found because of such scenarios, it can be addressed, and it can influence a better redundancy planning, a better development, and as well as a concurrent development for such chains itself. So if I have an independent functional chain that does not overlap, does not conflict with, or does not have a dependency on other functions, as a systems engineer, I might get into decomposing it further for to the unit level, or to whichever subsystem level applicable, system layer applicable, for decomposing that functional chain itself. So that could influence into, that could drive the engineering efforts towards such an engineering activity. And then the next thing being the documents being generated, the ICDs. So even these models being effective, that could be updated models for system level. They can be transferred to various discipline teams as documents, as we know, and such as ICDs, that can be driven from this one single source of truth at a system layer, from a system layer model. And we know that part of CubeSat development is also various reviews from CDRs, PDRs, or the mission assurance proof itself. Such documents can be required from the CubeSat developers to be presented. So if an elaborated and effective model is being placed in such a platform such as Capella, that is also a free or like open source tool, that could be accessible at any stage. It could further enable such knowledge sharing as well as consistent documentation as well. So ending with the conclusion, with this modeling effort, we went through a modeling approach from mission operations objective to an initial physical architecture. We saw added rigorousness in the analysis in SE adoption, involved in SE adoption, that could enable effective complexity management as Capella has a systematic methodology defined. It adds rigor and precision in terms of realizing from operational aspect to a system level element itself. And as we last discussed, the effective system models, the ones that are up to date, could further enable the knowledge sharing and the consistent documentation, which could reduce the efforts and time involved, even in repeatability aspect of the CubeSat mission, modifying the CubeSat functions itself for any other missions, or even for having a single source of truth that drives the qualification criteria for the elements being procured. So as a single source of truth for such models, it could be effective for the SE activities defined for the development. Thank you. Time for Q&A.
So thank you all for this presentation. Let me display the question we have. First question, pretty long one, but anyway. As far as I understood, the 3D behavior model helps with logical software validation, but with no appropriate physical outcome like position, control accuracy, or moment calculation. Is there any way to do so on Capella, or do we need to use a third-party application like Matlab?
So I can take on this question. With Capella, we do have a means to integrate such domain-specific or mathematical tools that can be used for a rigorous quantitative analysis, such as mentioned, the position control accuracy, the moment control. So such models do act as a means of integrating all such disciplinary analysis at one place at a system level. So Capella does, to answer that question, Capella does have a means to establish such analysis, quantitative analysis.
Okay, next question. So what is the approximate length of the full system model?
In terms of the
in terms of functional chains or model elements or things like that, I guess, or number of diagrams, probably.
Yeah, I do not exactly have the model element numbers as of yet.
Yeah.
Okay.
So
yeah, go ahead.
Okay, yeah. So in terms of full length of the system model, I believe it actually depends on the views and viewpoints that you want, or the kind of information that you want from the model, right? What is your scope of the model will actually help you define what the full system model would look like, or how many elements that you're going to use. So it's like uh, it's not a very definite answer, but yeah, it's the closest we can get in terms of what is the full length of the model. Yeah.
So how are non-functional requirements handled in Capella? Are there any spirit models created apart?
So for non-functional requirements, I believe you could actually define your model elements or the system elements that you're going to create. So you can add value properties, you can add data types to those values that you're going to define, right? So using that, you can actually enter your performance values or your tolerance values that you want to enter. And you could assign those to your system elements. Yeah. So that is a way in which you handle actually those requirements. You connect those requirements to your model elements. Yeah.
To add to that, Capella can be a means to have a trace with requirements that are being satisfied by various model elements or system elements. However, for managing, if that's what is being referred here, for managing, there will be various other tools like those that can be used. However, to have a trace of how much of requirements are being covered with the design, be it functional or non-functional, they can be modeled within Capella itself.
Yeah, I confirm there's a lot of ways to to manage that. And for those who might know, we had a very interesting presentation from Thales a few years ago at the Ecosystem Symposium about the specific integration between textual requirement and a Capella model. Okay, so can we generate electrical ICD? Well, I guess the question is, can we generate ICD from a physical model?
Okay. So I believe in terms of having a high level view of your ICDs and for your electrical components. Not like I don't know if you actually want to model your electrical components the into Capella and then try to link that to your very hardware specific high fidelity tools that you're going to use. So it's better to have a, a model element that actually helps you define at the system level of okay, what is needed, what interface is needed. But it would be a better choice if you actually program, or if you actually generate, not even generate, but if you actually have those electrical interfaces, like I'm talking about very specific, I'm talking about very hardware specific. I'm not talking about in terms of high level, like having your PCBs and PCBs connected to different components, right? So you can capture those in your model, but if you're going to go lower than that, if you're actually going to calculate the bits and you're actually going to calculate the power itself, I would recommend a high fidelity tool for that. Yep. Yep.
Okay, we have done with attendee questions, but I have one of my own.
Yeah.
I would be interested if you have details about the way you manage alternative trade-off, and basically, or you're able to maintain maybe, or have you did you have to maintain several versions of your model at the same time to make a trade-off, or don't you have to do that and maintain just one unique model? This kind of elements would be interesting for me.
To understand your question, I need some clarity on when you say versions. Is it with having alternate architectures for the system and different models for the trade-off itself?
Yeah, just have a few ideas about because you mentioned you had to select component at the end, and so I'm just interested in the process leading to choice.
Okay.
Yeah.
Yeah. Okay. So what comes to my mind is that we could actually make multiple of those diagrams, right? If we are going to have a logical architecture diagram, right? So maybe we could have one logical architecture diagram, but then I could have uh, two different architecture diagrams for two different components that I'm going to use. Yeah, but so that I can actually then manage on to connecting. At least I am connecting my logical elements to my physical elements, but then I also have the enumeration option that I can get uh, with in terms of performing those trade studies, in terms of then actually having the values of those components taken into tables and then perform calculations. But uh, like importing those outside.
Thank you.
Yeah. Thank you. Thank you,
Bye.
everyone.